Anyway, it's a great pleasure to introduce Chenyang Xu for his third talk on K-stability and Moduli of Fano Varieties.
Okay, thank you very much, Aaron. So I want to start with some, historical remarks. So, K-stability was a notion available to algebraic geometers maybe around early 2000. But as you probably see, the definition really, just from the definition, it's really not clear how to use it to construct a modular space. So I think the main motivation for people the main evidence for some people to believe there might be a construction is its relation to the Kähler-Einstein metric. But still, for many years, at least I was debating with myself, whether it's an analytic theory or not. For instance, even just 10 years ago, it was completely unclear to me whether there is an algebraic theory behind or not. I think I personally was convinced in 2018 when the uniqueness was settled. So nowadays I think many people live comfortably with the notion of K-moduli, but it was really not that clear just a few years ago. Okay, so today I want to talk about three topics: projectivity, local stability, and explicit examples. So I will start with projectivity. So I will first just outline how we prove projectivity of KSB or KSBI modular space. I think Jort will talk about this more in the next lecture. So I will roughly say, there are three big steps. So the first step is, Kähler has this package, which sometimes we call Kähler's package, to say that for this moduli, you just need to show that if you have a maximum variation family, the push forward of the vector bundle, the push forward of MKX, which is a vector bundle, is NF when M is very large. So once you prove this, then there's a way he can use Nakamura to prove the projectivity. And then this condition is confirmed by Fujino 2012 that this is really NF. However, this is only enough to deal with the non-pair case. So if you want to deal with the pair case, there is a lot more. There's an extra subtlety that you have to deal with the divider, and because the Lie bundle is not functorial on the divider, you have to do a lot of work, and that was settled by Kovac and Patkvavi 10 years ago. Then, I added the last part only because it's somewhat related to today's topic. So Patkvavi and I show that the same Lie bundle which is the leading term of the Lie bundle in Kähler's construction is actually also B. So you can use the same Lie bundle to get the projectivity, but the argument depends a lot on the Kovac-Patkvavi's work. But now we turn to Fano variety. So we also first want to get the same Lie bundle on the Fano variety. Actually, this can be defined for any family of n-dimensional Fano varieties. So basically, we just push forward the. There should be a determinant here. The determinant of this Lie bundle, you can just take the Mumford-Knudsen expansion, and then you have this term. And then again, the leading term, but now we take the inverse, which is the same Lie bundle. If your Kx is Q Lie bundle, then this is you have to scale it and scale back, and then you get a Q Lie bundle. But it's not a big deal. And if B is normal, actually this Lie bundle can be very easy to see. It's just the push forward of this. So here you intersect n+1 times. Then you push forward, that's a codimension 1 cycle on the base. Actually, you can show it's a Cartier divisor, and that Cartier divisor is the same Lie bundle. So then, this can be defined for any family of n-dimensional Fano varieties, and because of the functorial property, it actually can be defined on an infinite type substack of this. The infinite type because I need the scaling factor to be uniform, and so particularly if I restrict on the open stack, which is the K-semi-stable one, I got this lambda Cn. So then I can further descend this lambda sum to the good modular space. I mean, the reason is the orthonormal group of, I mean, the connected part of each point, the inertial group acts on the lie bundle trivially. And then you can descend to the lie bundle. So somehow to get to the productivity of this guy is difficult because it's only positive on this locus, this semi-stable locus. If you move out this locus, then it's not positive anymore. So your proof has to combine the fact, I mean, the higher dimensional geometry with some K-stability theory. And fortunately, we got able to prove this, that, I mean, basically it's a two work. First, Cologoni and Kafavi, they made some breakthrough, and then Zichuan and I, we completed the proof. So basically, we show that the same lie bundle descent to the K-modular space is actually ample. So particularly, because yesterday we already showed it's proper, so it's projective. I mean, you may wonder why we expected this lie bundle to be positive. I mean, there was some reason, also, again, coming from the Kähler-Einstein metric side. I mean, that was observed by different geometers for a long time, for instance, like Tian. And I mean, the second remark is what I just said, that this same lie bundle is actually not positive if you don't have a stability condition. So somehow the proof has to incorporate the stability condition. So again, I mean, the art of, I mean, studying K-stability is once you assume your thing to be K-stable, you have to find some like specific divider or specific filtration to prove what the properties you want to prove. So here the filtration we want to use is coming from the Hadana-Shimohan filtration. So let's for simplicity, let me first work over a curve. So then if I have a family of Fano variety over a smooth projective curve, of course I can just push forward this, and then I got a vector bundle, which is an AM, I write it. And then I can just filter it by its Hadana-Shimohan piece. So, and I define the filtration of this vector bundle. I mean, the jumping number, I just define to be precisely the slope. And this is for the filtration for the vector bundle. If I want to do a filtration for a single Fano variety, I just look at the image. So it's a little bit similar to what I did yesterday. I look at the filtration of the vector bundle, and then I restrict on one fiber, which is the fiber will be, of course, just coordinate ring of the corresponding Fano varieties. And actually, asymptotically, there is another equivalence description of this filtration. Is I just look at the global image like this. So for fixed lambda, and then I restrict on a fiber. I look at the possible image, and you can easily prove that basically they bound each other. So asymptotically, from the K-stability viewpoint, you can regard these two filtrations to be the same one. So now we do some calculation on the constants. So if I do the SM, the way I define the filtration, if you take the gradient sum, it's precisely just the degree of the vector bundle. So that means the SMG is precisely just the degree of the vector bundle divides by the number m times the dimension im. So the SM is very easy to calculate. And then, of course, you take the limit. Remember, the same lie bundle is a leading term of this expansion. Then you just got the negative of the leading term of the expansion. So you just got this formula. I mean, this is relatively easy to calculate.
And you can't see because of
Okay. Sorry. I mean, I can see on my iPad. That's why, but because my iPad, I don't have this little screen there. Yeah. Okay. So this is what we calculate, the same degree, and now the first observation is that for any family of Fano varieties, no semi-stability condition is required. The mu I defined yesterday is always non-positive. I mean, the reason is now I interpret this filtration as the second one. Then that means if the mu is positive for m very large, I can find the gamma such inside this, which is coming from the global restriction, right? That's my definition of the second filtration. And then, because mu is precisely characterized when it's low canonical or not, that means this pair, if I restrict on the special fiber, it's low canonic. But then that's contradiction, because I have if I take the kx plus 1 over m lambda gamma, it's 0. So by for instance, by this kind of standard positivity, that means we know that the kx plus 1 over m gamma has to be positive. But on the other hand, it's a pullback of negative f, which is negative. That's contradiction. So this holds for any family of Fano varieties. The mu is always non-positive. But the fact is, if xt is k semi-stable, then mu minus s has to be non-negative. But s is the minus of the degree, so that implies this guy is positive, non-negative. So we got the naiveness. So somehow the naiveness comes from the combined two positivities. One is the positivity of the for any family of Fano varieties. That's kind of a standard positivity from the high dimension geometry, and another one is the semi-stability. So if we want to prove ampleness, I mean, we want to, again, mimic the Collas package. So then we want to show this guy, not just the determinant is positive, it's actually a Nav vector bundle. That's actually, of course, a certain, stronger assumption. So how do we do? Let's first assume that the fiber is uniformly K-stable. So then, if the delta is delta x, we actually can prove that the mu delta is larger than s. Here, mu delta is was originally defined when the delta is equal to 1. But now we can choose a larger delta and also define the same number. So remember, mu is a decreasing function. So if I put a delta, decreasing function of delta. So if I put a delta larger than 1, a priori this mu is smaller. But since it's uniform stability, we still have a mu is larger than s. I mean, this requires some proof, but we know that. So then I just apply the same idea again. I can just find a divisor d, which is like 1 over m gamma in my previous argument, linear equivalent to minus k minus sf, such that the x delta d is LC. So I mean, again, this LC condition comes from the definition of mu. And then if I take the sum of this, so first I have a pair, which if I restrict on a special fiber, general fiber, it's LC. Then I know if I push forward downstairs for large multiple, it's Nav by Fujita-Kawamata semi-positivity. But the same push forward, is just linear equivalent to this one. So here, delta is larger than 1 plays a key role, because then it's basically of the form, the push forward of minus k, some multiple of kx over c times some lambda f. So our goal is to prove lambda f is ample. So instead of this guy Neff, this one is Neff. That's good enough, because if we take the determinant, we just got a larger multiple of lambda f, but it's still the gadget we want to prove ampleness. So that's the proof how when xt is uniformly K-stable. But unfortunately, in general, if xt is K-polystable, there is no way you can hope this guy is always Neff. I mean, a simple example is I just take the hittable surface over P1. And if you push forward, I mean, this is a trivial family of P1. I mean, fiber is a trivial family. I mean, locally trivial family over P1. So this part is 0. So this part doesn't play any role. You just compute this part. Of course, we know the push forward is not just O. It's a sum of like O1 or negative 1, O2 or negative 2, this kind of thing. But what we can do is we can twist this family to P1 plus P1. Then you push forward, the vector bundle become balanced. It's just O everywhere. Then it's NF. So we want to incorporate this idea for general family of Fano varieties. So somehow we want to twist it. But where does this twist come from? So here, first, let me define that if I have a torus action, so now, since we're doing K-polis demonstration, we can assume, we can basically boil down to the case that we have a torus action on every fiber. And for torus action on Fano variety, you can for any filtration on the gradient ring, you can define a twisted filtration by just define this way. So basically, I mean, I think this was mentioned in Matthias' talk. So you can twist your in Sab's talk. So you can twist your filtration, and also for the Kasi, I mean, Kasi now lives in the dual of the weight space, so it's a co-weight. But sometimes we also think about the tensor R, so the real vector coefficient case. So that's the vectors. That's basically just the vectors on torus. And for any co-weight, we can also twist our family for fixed P in this way. So basically, we push for the A alpha, but now we don't take approach of A alpha. We take approach of this guy. Here I use the fact that the torus acts on the fiber, fiberwisely acts on the family. So then I can take this new family, the twist family, which is I write as XC. And then there's a same filtration. I can study the same filtration. And the same filtration of this guy is precisely the twist of the original same filtration. So that means, roughly speaking, the twist commutes with you take the same filtration. And the same degree will be the same as long as the Futaki invariant on the fiber is 0. This is always true if our fibers are semi-stable or K-polystable. Then here, again, we use this finite generation very deeply, is that basically the K-polystable version is equivalent to the uniform version of K-polystability. The uniform version say there again exists a lambda larger than 1, such that for any filtration F, we can find the Kasi, which satisfy this. So basically, this is the uniform version of K-polystability, and the equivalence of this two is a highly non-trivial statement. I mean, that need high rank fine generation. And now I can twist X by this Kasi. And since now we are really have this condition for our same line bundle, then I can use the argument in the previous slide to get this. So we have this condition. Now we can twist this to get this condition, and then we can apply the argument in exactly the same way as the previous page. So in the previous page, I basically say that if you have this condition, then you get the definiteness of the push forward as a vector bundle, and here it's the same thing. So what I'm doing, basically, I just twist back this family into P1 cos P1. And this twisting is dictated by this Kasi here. This Kasi to choose to satisfy this inequality. Somehow this K-stability will force you to find the right twist, and the right twist will make this work. And then the push forward will become NF, and then you can go along to prove the ampleness of the same line bundle. So that's how we prove the ampleness of the same line bundle. So next, I want to turn to some seems very different, but actually philosophically very connected topic, which is local stability theory. So this is not about the Fano variety. I mean, for our higher dimensional geometers, we always know there is kind of a global local correspondence. So global object will be Fano varieties. The local object will be KOT Fano varieties. I mean, what I mean there are many results. Once you prove the global version, you naturally ask the local version. So then you might naturally ask yourself, whether there's, since we have this stability theory for Fano variety, whether there is some kind of stability theory for KOT singularities. And the answer is yes, we do. So I start with adding KOTs, local singularity. And I now, instead of looking at all the valuations, I look at the valuations which is centered on this point. So again, this is a space of valuations. So a while ago, and Latterfeld Smith, they defined a notion called the volume of this. So for any valuation, you just look at the valuative ideal, and then you let this lambda, this value, go to infinity, and you calculate the limit of this number. That's just the volume. So you usually say that if you scale your valuation v by lambda v, then the volume goes to the 1 over lambda power 2n. So, however, the key definition in this theory was first found by Chili. Actually, I think he was somewhat inspired by Donaldson and Song's work. And actually, Song was talking about this work it's 10 years ago in the same summer research institute. And Chili and I actually, we do have some conversation on that. And I actually asked him whether there was a local stability theory. And then he went back and spent a few months, and then he found the really the right one. So basically, we define the normalized volume to be this gadget. So here we scale this volume by the nth power of the log discrepancy. So as I already mentioned before, that the log discrepancy was originally defined for divisor, but you can extend to the space of all valuations lower semi-continuously. That was done by Johnson Mustata. And so then I define a volume of singularity as an infimum of all possible normalized volume for valuations over this. So now we have a sequence of results which are parallel, maybe except one, or then are all in some sense parallel to the global stability theory. So again, we are in a kind of question that we have a function defined on the space of valuations, and we try to minimize this. And then for the minimizer, we want to study some geometry of that. That was exactly, I mean, we did this for the delta function on Fano variety. So here we do this for KOT singularity. And it was first proved that by Harrow that this guy has a minimizer. And then again, I proved this guy minimizer is comonomial. Actually, in this case, it's really comonomial. It's not that, I mean, there are examples that there are no divisorial valuations to be minimizer. I mean, the simple example is you just take a cone over the F1, the hitable surface. Then if you compute the minimizer, it's not divisorial. Actually, the minimizer is, in this case, is unique up to rescaling. I mean, I should say that the normalized volume is rescaling invariant. So if the normalized volume of lambda v is the same as the normalized volume of v. So the best you can expect for uniqueness is the unique up to rescaling. And again, we prove that the associated gradient ring is finite generated for this minimizer. Again, I mean, of course, for general valuation, there is no reason the gradient ring could be finite generated, but for minimizer, it is. And we actually also show that if you look at this minimizer, you take the spec, then got a affine variety, and then there is a torus action on this affine variety, together with one special real co-weight coming from the valuation. And if you put this data together, this X0 C, it's K semi-stable. So here I didn't define what this K semi-stable is. I mean, there's a analog. I mean, there's a definition of K semi-stability in this setting. I think first introduced by Collins and Sacchidi, which I mean is closely related to whether there is a Sasaki-Einstein metric, but there's a local version corresponding to that. But let me say a little bit about the uniqueness here, because this is a new phenomenon. Delta is really not unique in general. So of course, how do you show uniqueness? I mean, since you want to Sebastian and Matthias talk, you know you want to get convexity. So I want to get convexity for this normalized volume function. But of course, for valuations, we cannot connect them. You know, if I pick up two valuations, if I write down the naive connection to connect them, then usually it's not a valuation. So there is no natural path to connect the valuation. So somehow you have to embed this valuation space to a larger space called the space of filter ideals. And then you get a similar function, which is the normalized multiplicity. And you show this function is actually strictly convex. And that was the idea in the Bloom, Liu, and the Qi's work. So then the next natural question is, what is the set of all the possible volumes? So if it's dimension 2, then it's all quotient singularity. I mean, we want to compute this, of course, and we want to possibly put them together. And in dimension 2, all of them are quotient singularity. And for quotient singularity, we know that the normalized volume is actually the normalized volume of the smooth one, which is n power to n, divided by the degree. Actually, this is true for any quasi-automorphism. But how about higher dimension? I mean, this is still wide open. We have not many idea of what are the numbers even in dimension 3. But Zhichuan and I proved that this set is essentially discrete, except it could go to 0. So somehow, if you take any one of them, if you ask what's the one below that, then there's a gap. So each time you have a gap, there. And so how to prove this? So the previous slides, which we call stable degeneration, this is actually a process preserve the volume. So starting from any singularity, I can just degenerate to the spec. The x0, let me remind you, is this one, the spec of this guy. So for any x, I can degenerate to this x0 using this process, using this theorem, this stable degeneration theorem. And then we actually know that this process preserves the volume. So if, in other words, if I just want to look at the volume of the general arbitrary singularity, it's enough to just look at the singularities, look at the volumes of this type of singularities, because this process preserves the volume. And then we prove that if I fix a number delta, I look at the singularities, this kind of, we call Fano cone singularities with a volume larger than this delta. And this Fano cone is K semi-stable. All such set is again bounded. This is what Zhichuan and I proved last year. And again, in the proof, we need Berkowitz theorem on boundedness of complements. So somehow the Berkowitz theorem on boundedness of complements play another role in this K-stability theory. I mean, this time it's local. Actually, it's also play a role in my proof of the minimizer is cosimonomial. But so, I mean, what's the application of this local singularities? So I think the first application people found is the connection with the global one. So you have a global Fano K semi-stable variety. For any singularity, I put on then there is this inequality. So here n is a dimension. So in particular, if I take x to be a smooth point, I mean, of course, you always have a smooth point. Then I conclude that any K semi-stable Fano variety, the volume, remember the smooth guy, the volume is n power to n. Then that means the volume of this guy is less than n plus 1 power to n. So then you prove that any K semi-stable Fano, the volume is at the most n plus 1 power to n. This was Fujita's original theorem. And Yu Chen basically upgraded the Fujita theorem into the singular version. And so we're also interested in some like precise numbers of the volume. I mean, it's relatively, I mean, this result is relatively easy to prove that, I mean, the largest one is the volume of the smooth, which is m power to n. And then from what Zichuan and I proved, we know that the second largest one, I mean, there will be a gap, but the conjecture is it should be the volume of the most mild singularity, which is just A1 singularity. And then if you compute the volume of that guy, is 2n minus 1 power to n. But unfortunately, this is only known up to dimension 3. And I mention this because I will use this. I will both use this, I mean, Fujita-Liu's inequality and also the fact that we know this up to dimension 3. I mean, there is a very recent, very interesting work on applying this to minimal program. So by Han Liu Qi Zhuang. So if you start with the KOT general type variety, then I can just define the alpha invariant. I mean, alpha invariant, we talk about the for Fano, but you can define essentially for any linear system, non-empty linear system. Here I started for Kx. And then it's relatively easy to prove that the normalized volume will be larger or equal to the volume of the Kx and the alpha invariant power to n. So I mean, this is not very hard to prove. But if I run any MMP sequence, then of course the alpha invariant will not increase or will not decrease. So in any step, the alpha is star is bigger than larger or equal to the alpha invariant you start with. Then that means this guy is bounded, and the volume of Kx doesn't change, of course. Then that means that actually for any singularity in this MMP sequence, the normalized volume is bounded from below. So we have a study MMP for many years, and previously the only, I mean the most popular invariant attached to it is study MLD, and we know MLD has some monotonicity. Here we don't. I mean, the normalized volume might not have a monotonicity, but it at least has some kind of boundedness. And this boundedness will give you actually many other boundedness without. So for instance, Zichuan and I prove that the local fundamental group is always bounded above by some number divided by, some constant divided by this normalized volume. So if your normalized volume has a lower bound, this local fundamental group has the upper bound. So that particularly implies any weight divisor, any Q Katia weight divisor, it has a uniform Katia index. So if you apply this to Kx, the Gaussian index is uniform. So I think this was not known, I mean, in any previous work of MMP. And also, Zichuan and I proved that if the normal volume is bounded from below, actually the MLD is bounded from above. So the previous one tells you the MLD in that sequence, the denominator is bounded. And the second one tells me actually the MLD is bounded from above. Then that means the MLD only actually lives in a finite set. So somehow, I mean, this beautiful work really connects the study of K-stability with minimal program, and the connection is quite nice. And here I pose a question that can we prove that the termination of MMP just using these techniques, at least in the case when Kx is big. So I mean, this is my thought about the high dimension geometry. I mean, the foundation is minimum program. I mean, I think, for instance, there was this milestone result by BCHM 20 years ago. And then since then, there is a huge progress on boundedness of general type varieties, boundedness of Fano varieties. And to get those results, you need a minimum program. And then in the last decade, there was this development of K-stability. And for K-stability, we need both MMP and boundedness. I mean, there was some philosophical idea for people to believe that we can use boundedness to attack MMP. more precisely to attack termination of flips. But somehow this philosophy was really never really realized, at least as far as I know. So, but maybe the one to get the boundaries to get termination of flips from boundaries is via K-stability. So somehow there might be a third leg in the story. Now we start to disclose. So I hope in the conference 235, somebody can tell us how to prove termination flips. And I even hope that uses K-stability. Okay, I have talked about K-stability for 3 lectures. Now I want to give you some explicit examples. So in 2015, Donaldson gave a series of lectures about his work with Chenyang Xu and also independent by Tian about this existence of Kähler-Einstein metric for K-stable Fano manifolds. But in their third paper, Chenyang Xu, they write a series of 3 papers. In the third paper, they explicitly mention that even they prove this equivalence, they cannot, as far as they know, there is no single example people establish K-stability algebraically before people actually already know the existence of Kähler-Einstein metric. But they were expecting that the things could change in the next few years. And let me here to tell you that their expectation is actually correct. So now, of course, we even have a moduli. So then we basically, I give you any family of Fano variety. You can ask you some 3 questions. First, whether the general member of this is K-semi-stable. If it is, then we know there is a Zariski open set by openness. And then there might be some particularly interesting one. You want to show the K-stability. That might require more work. For instance, you want to show all the smooth members in this family is K-stable. And the last one, of course, is get a complete description of this moduli. I would say in general, to have the complete description of the K-moduli in higher dimension is complicated, it's hard. But we do have some examples. If you compare the situation with K-SBA moduli, specific examples of K-SBA moduli, I would say the situation for K-moduli actually looks much better. We actually have more examples in the K-moduli side. That probably is related to the fact that when you study the degeneration of Fano varieties, the degeneration is relatively mild than the degeneration in the case when Kx is ample. So, but the big leading conjecture in this field, again, this is something I hope 10 years later people can talk about this, is that all smooth degree D Fano hypersurface are K-stable, at least when D larger than 3. 1, 2 are just trivial. So, well, to be honest, there is not much philosophical reason to believe this is true. But on the other hand, so far, we don't have find any kind of example. And somehow, I think it's just very natural to expect all the smooth hypersurface to have a Kähler-Einstein. We know it's GIT stable for the natural embedding, but I don't think that's a very strong evidence. But even harder question is what is the commodification? Because we know the general members are K-stable. So there is definitely a K-moduli whose general members parameterize hypersurface. But then you can ask what's the commodification? So, as I said, we know a lot more than 10 years ago, but there are still many we don't know. I will use the cubic threefolds as an example to give you some feeling of how to get this. There are many other work. So first, let me tell you how to show a general hypersurface is K-stable. There are many ways to prove it, but let's use this beautiful theorem by Zhuang that K-stability is actually the same as equivalent K-stability. So if there is a group acting on your variety, you only need to study everything equivalently. So for test conversion, just study the equivalent test conversion. For valuation, just study the G invariant valuation. So particularly, we know that there is a mu D action on the degree D from a hypersurface. Then I just take the quotient. The quotient will be Pn with n plus 2 hypersurface with the coefficient of 1 minus d1 over d. But then by simple interpolation, you know that this guy is actually K-stable when d is larger than 3. So then you just got the Fermat hypersurface is K-stable. Then you know there's an open set is K-stable. But how about others? So let's take the example of cubic threefold. So basically we aim, I mean, Yucheng and I show that this is the K moduli in this case is the same as GIT moduli. And to get this upshot is to show, because we already know the K moduli is a proper guy. So you always have a limit. But we have to show that all the limit lives in P4. I mean, the entire business of the explicit study of K-stability is to find a nice projective geometric characterization of the limit. So often it could be very complicated. For instance, if you look at the cortical case, often usually the limit will not be in the same PN anymore. So you really have to go out. But fortunately in the cubic case, we expect it's always still in the same PN. And then how to show this? So I mean, once you can show this, then a simple result by Powell and Xiangpao and Tian says that K-stability is the same as GIT stability. So we just boil down to show that the limit is always in P4. And Fujita showed that it's different than Fujita. Show that the normal limit x of cubic hypersurface, if you want to show its cubic hypersurface, you only need to show that the degeneration of O1 is Katia. So we know that the degeneration of O1 will be a weight divisor, which is Q Katia, but they actually want to show it's still Katia. So, and the Fujita-Liu's inequality, which I mentioned a few minutes ago, says that if x is K-semi-stable on the limit, any singularity has to satisfy this inequality. Here, I just use the fact that I know the volume of a cubic hypersurface. So then, if my goal is to show that the L is Katia, so I want to show that, for instance, if the pi1 local pi1 is trivial, that's definitely good enough. So if local pi1 is not trivial, then I can take a universal cover. Then by the finite degree, I know the volume will go up by the same degree. So if it's 2, it's just 2 times this number. It's already 6 of this number. It's already larger than the supposedly second largest volume. So then that means the cover has to be smooth. But then that means the singularity has to be coefficient singularity. But we usually don't have a coefficient singularity deformed to smooth guy, at least when it's coefficient 3. Right? We know that for 3-dimensional isolated singularity or above isolated singularity, when you deform it, it cannot deform to a smooth guy. And then there is some either way to deal with the 2-dimensional case, because this same proof also tells you even though there is a fundamental group, it's at most Z mod 2Z. Then the opposite, the singularity is something like 1 over 2, 1, 1 times the rest. So once you know this fact, that then you get the universal cover is smooth, then basically you are done. But unfortunately, we only know this up to dimension 3. That's why we can only prove this dimension 3. So if you prove the gap conjecture, then the consequence will be the cubic is the same as the K moduli is the same as GIT moduli in that dimension. So this strategy has been applied to many other cases. Actually, even before our work, before all this exists of K modular algebraic work, analytically, this was already used by Mabuchi Mukai to deal with the degree 4 dipolar surface and Odaka Spotty Sun for degree 1 to other dipolar surface. And Asher, De Fleming, Liu, they wrote a series of 3 papers to study the log case. And particularly they work out the case of P2 with a curve, P1 plus P1 with a curve, and P3 with a degree 4 surface. And along the way, they actually develop a general framework of wall crossing when you change the coefficients. So there is really a wall crossing for them. I mean, now many people are working on this along this strategy. And also, Yucheng, I mean, even we don't know the gap conjecture in dimension 4, but Yucheng has some nice way to prove that the cubic fourfold, the GIT is also the same as K. But there's another approach to directly estimate the delta. And that's called the Abendron method. So using this method, they got so far the strongest result for hypersurface. So basically they prove that in this range, the any smooth hypersurface is K-stable. So this N is for any N. So and as I said, the key recipe is something called the Abendron method. And this boils down to something, I mean, to inversion of a junction. So basically, we can use the basis type divider to estimate the delta. So if I want to show the delta has minimum delta 0, I just need to show this kind of thing. But if I can find the divider E, such that first I need to check that if I want to show delta is larger than delta 0, of course I have to check for this E, A over S to be larger than delta 0. And then I can extract this E and put a coefficient 1 in front of that and do the inversion of a junction, do the reduction step. So after the reduction step, then you have to estimate the delta of the restriction pair. And then if you have the restriction pair is low canonic, then you know by inversion of junction, the original one is low canonic. And that's good enough to prove that the delta event has delta. If you can do this for all the delta m, which is compatible with E. So the business here is that if you choose this E closer to the divider, which estimates delta, this step is closer to if and only if. So somehow, if you know what you should compute delta, then you just riff on that. Then you just work on that. You don't lose any information. If you choose a random E, then you might lose a lot, but you might be still able to prove something. So in Abendron's case, to hypersurface, they actually choose a pretty random E. They just choose the E to be the X intersected with the hyperplane. And then they just keep doing this step again and again. The main difference is when you reach down E, you don't get a linear series, you get a multi-gradient linear series. So you have to estimate that. And here, because they choose this pretty easy hypersurface edge, although it's not far, it's very far from to get the best estimate, but it's relatively, I mean, compared to other cases, one is able to estimate this delta for this gradient linear series, and then they all the way cut down to curve on the surface and get the delta. So then this machine is actually found to be very powerful for the straight folds. So because in that case, the E is dimension 2. So you reach on E, you can just study the dynamic decomposition and so on. So it's really, you have a lot of way to estimate the LCT on the E. So now, once you have this method, and then you have many other methods, you can start to go through this Iskovsky-Mori-Mukai's classification of the 105 families. So arguably, the most interesting case is the Picard number 1 case. And Abendron, they show that except the family 1.9, 1.10, which is, in my case, is equal to H, and the HQ self-intersection is 80 and 22. All other smooth Fano threefolds with Picard number 1 are K-stable or K-polystable. So we actually conjecture every smooth member in this family should be K-semi-stable. I mean, there are just 2 families. But we know that in 1.10, there is some strictly semi-stable guy. So you cannot expect all of them to be K-polystable. Actually, this family 1.10 is of historical interest. That was in the paper when Tian introduced the notion of K-stability. And also Donaldson also wrote some like a conjecture on this one. So, and then there is this book by Arroyo, Castrava, Chersoff, Fujita, Kalagoris, Martinez, Garcia, Shramov, Seuss, and Vestevani. Actually, I don't know how to, no, sorry, I forget how to pronounce the last name. So I'm sorry, yeah. So there are precisely 79 families out of the 105 whose general member is K polystable. I mean, they really have a list of which one is not. And now Cherenkov and many others are actually working on Fano threefolds with row larger than 1. But actually, I encourage them to look at the 1.2 and 1.10 because I think the Panama 1 case is the most interesting case. Okay, so let me just mention there are some other very interesting Fano varieties which people want to prove they are K-stable. Here I list two coming from somewhat different theory. The first one is just basically the module of the vector bundle, and we expect it to be K-stable. I mean, there's some in the rank 2 case. There is some result by. Okay, it's James McCann student. Sorry, I forget his name. Yeah. So, I'm sorry. Yeah, but in general rank, there's absolutely no result. And also, LeBron a while ago conjectured that all contact Fano manifolds has Kähler-Einstein. And now you can also just interpret that to be all contact Fano varieties is K polystable. Okay, thank you very much.